Okay, so it's very happy to come here again to give you um, my talk series on database theory. It's been a while. In the past few weeks, I've been teaching. Okay, so now I'm done with my teaching, so I'm resuming the seminars. All right. Um, well, before the break, we finished a grand topic on approximate nearest neighbor search. All right, so starting from today, we'll talk about a new topic, right? So the topic is about sampling. Okay. So I plan to do a systematic introduction to sampling, starting with the foundations. All right. So today I'm going to talk about something very, very fundamental. Probably you have heard about the relevant concepts before. So this is about WOR and WR sampling. Okay. I'm going to formally define these notions in a little bit. All right, so bear with me until then. Um, for today's talk, I'm going to look at a set of elements. So let's say this is denoted uh, as S. Okay, so the number of elements is n. Okay, so I have n elements here, right? Okay. So I want to do sampling, right? There are two sampling schemes here. First one is sampling without replacement. Okay, so this is without replacement. Okay, so this is WOR for sure. Okay, so what do I mean by this? Well, if you want to perform this operation, you need to specify sample size. Okay, how many sample elements you want. Okay, so this is an integer. So this k is an integer uh, in the range from 1 to n. Okay, so this is something that you give in advance, and then an algorithm will have to give you the sample, right? The sample set. Sometimes I just refer to that as a sample, right? So this sample is a K subset, okay? Now here, this is a relevant notion. So what is a K subset? Okay, so let's do it here. So the meaning of a K subset of S is, this is a subset of S having size K. In other words, you would have, you have exactly K elements in this subset. All right. So if I ask you how many K subsets there are, right, for a specific value of K, well, everybody knows you've got N choose K, such kind of subsets. All right, good. Now, I'm ready to define the output of this WOR sampling. So this WOR sampling is a K subset drawn from all the possible K subsets uniformly at random. Okay. Okay. So in other words, if you look at the output of this operation, that's a random variable. Okay, so this random variable is drawn from this population, and this population is, the collection of all the possible K subsets, right? The size of the populations and choose K, right? So each one of them has exactly the same probability of being returned. Okay, so this is the formal definition of without sampling. Okay. Um, okay. A very, very relevant concept is with replacement. WR. Okay. So once again, you have to give a parameter So this time, this parameter can be anything. Typically, we will talk about, something from 1 to n, because usually when you sample, you don't want the entire population, right? So you just want a bunch of elements. So typically, the number of elements you want to get is, something way less than n, right? Okay, so let's say in general it's k. So of what is the output of a of this operation? Okay, so this is saying this is a sequence. Okay, it's a sequence. Okay, um, a sequence chosen uniformly at random. Uniformly at random from what? From the following set. Can I watch calculator? This is S to the power of K. Okay. Well, I can see some people are nodding, but not everyone. Okay. So what this essentially says is that, you can think about this Cartesian product, right? So S times S, and then you have to do it um, for K copies of S, right? So this is essential. So if you look at every element in this, Sk, right? So this is essentially a sequence, right? So E1, E2 to Ek, right? It's a sequence. Every element inside this collection, this family denoted as h to the power of k. So this is a sequence. Okay, so every EI can be independently taken from this population S, right? So if you look at the size of this family, okay, so if I say okay, how many elements there are, in other words, how many different sequences there are in family, you should tell me that's precisely n to the power of k, right? So if you look at the definition here, the output of this WR sampling should be the sequence chosen from this S power of k uniformly at random. Okay, so exactly every possible sequence in this S to the power of k will have to get returned with exactly the same probability. Okay, so as you can see, one key difference between WOR sampling and this WR sampling is that the output of the former cannot contain duplicates, right? Because it really has to be a K subset, right? On the other hand, for WR, this obviously doesn't have to be the case. Nevertheless, WR gives you independence. You see what I'm saying? Independence, right? So you can look at this WR. Essentially, you can think about it as K independent operations, all right? K, right? K is the number of the sample size here, right? The number of elements you like to take. You can conceptually think about it as, doing the following experiment k times, and every experiment just draws one element from this set as uniformly at random, right? So you do it k independent, you do it k times independently, right? Whereas you cannot say that the elements returned by a WOR sampling are independent from each other, because they are not, right? Because they are not, because every element um, well, if an element is there and then basically has occupied one seat, right? So the other elements, it will. So clearly there are correlations among the elements there. Okay, cool. So this is basically the foundation of everything. Every time you talk about sampling, you have to be familiar with these two notions. Okay, so we're going to start from here. Okay, so I expect to spend quite a few seminars on this. I guess maybe. Well, if you also talk about the sampling problems related to database systems, I would say probably I will spend maybe 10 hours on this. Okay, roughly speaking. All right, so this is the first hour. Okay, cool. Now let's think about algorithms. Okay, let's think about algorithms. All right. So if I say, hey, WR, that's pretty easy, right? That's pretty easy. Well, in order to really talk about time, I have to make certain clarification about, this computation model that I'll be using, okay? So I will assume there is an oracle, and this oracle allows me to generate a random number in constant time. Okay, so more specifically, for today's purpose, this oracle will have to generate a random integer. Okay, so basically in the form of 1 to some t, that specifies an interval range, and I say I want a random element, uniformly random element. Okay. From this range. All right. So this should take constant time. All right. So I'm not going to discuss how to implement this. I'll be assuming, I have such an operation. In addition, I will also be assuming that the set S is stored in an array to start with. Okay. And other than that, I'll be using the standard operations in the RAM model. Okay. All right. So if that's the case, WR sampling is trivial, right? Because as I said, you only have to do this thing k times independently, and each time just have to generate a random number from 1 to n, right? And then you just go to the position. Let's say the random number is r. Just go to the position in this array, right? So every sample element can be taken in constant time. So overall, you can do things in k time. Okay, good, very nice. All right. WOR, on the other hand, deserves more attention. Okay. So we will embark on a journey that will allow us to see a lot of things along the way. Okay. So first of all, I'm going to give you something that appears to be inferior in terms of computation time. Actually, the first few algorithms, the first two algorithms, will have n time. Okay, to do this WOR sampling. And then eventually, I'm going to give you an algorithm that takes k time in expectation. But this is not to say that the final algorithm wins all right? So the final algorithm, this k time algorithm is not really a slam dunk winner in the sense that actually the first two algorithms, they do have very interesting properties. Okay, so all these things will be clear in the end. Okay. All right, so let's get things started. So I'm going to talk about WOR sampling. However, I'm going to take a detour to do so. Okay, I will depart from this sampling scenario for now. Instead, I will talk about a very, very relevant problem, which is called permutation. Okay, random permutation. Okay. All right, so this is, once again, a problem that can be defined on any set of elements. You see, what those elements are, does not really matter, right? So here, if I talk about random permutation, essentially I'm saying, well, the input is this set S, and I want you to generate another array at the end of this algorithm, okay? So this array should store the elements of S in a certain permutation, right? So if you think about it, how many permutations there are, there are n factorial permutations of the elements in S. So essentially, I'm saying each of those permutations would have to get returned with exactly the same probability. Okay, so that is the problem of random permutation. Okay, all right. The first algorithm we will discuss is called this Fisher Yates shuffle. Okay, Fisher Yates shuffle. Okay, FY shuffle for short. Okay, so this is actually the starting point of WOR sampling. Okay, so once you understand how this algorithm works, and then you will understand how several other algorithms work for WOR sampling, as you will see. Okay. All right, so let's talk about this algorithm. Okay, so here, originally we have this array A. So this is an array storing S. Okay, so in the beginning, I have no control on the initial permutation of these elements. All right, so you can give them to me in any way you want. But in the end, I'm going to turn this A into a random permutation, guaranteed. Okay, So clearly, this cannot be a deterministic algorithm. See what I'm saying? Because the output will have to be a random variable, right? So the whole algorithm will have to be randomized. Okay. So the algorithm says the following. You know what? I'm gonna look at every element in turn. Okay, as if from I to n, there are n elements there, right? So let's look at this for loop, the ith iteration of this for loop. So here, what you want to do is you want to generate a random number. So this random number, let's say a random integer, from 1 to I. Okay, so this is the ith iteration, okay? Ith. So I have I there, right? And I want to generate a random integer from 1 to I. And as I said, this can be done in constant time, and I don't want to know how, because that's an oracle I'm assuming here. So I get this R, right? I get this R, okay? And then what you're going to do is you want to swap the position of AI, which is the last element you're looking at, right? Because we're talking about the ith operation. So this is sort of like the new element you're processing. So you want to swap AI with a R. Okay, R is the number that R is this random number that you just obtained specifically for this iteration, right? So the next iteration will have its own random number, but that's what, I mean, that's everything, and that's what happens within this iteration. Okay. So very well, if you look at it, you can see that this R and I, if they happen to be the same, and then the swap has no effect, right? Otherwise, it will change the positions of those two elements. So this is it. Okay, this is it. All right. So you can see it's very simple algorithm, and obviously the running time is big O of n. Okay. All right. Well, algorithms, they are only 50% of the story. All right. So why does this algorithm work? Okay. So let's prove it. Okay. So this is, I would say, not something that everybody understands, but I would like to go into the proof because after all, we want to go a little bit deeper, right? And also, I want you to understand why this algorithm really, gives you a chance to generate all the possible permutations, right? So that understanding will help when you think about sampling. Okay. All right, so we have to prove that the algorithm is correct. Okay, so the lemma, the statement that we're going to prove is the final A is a random permutation of the original set. Okay. So in order to prove this, we have to prove that every single permutation of the set has exactly the same probability to be output, right? So I allow you to fix an arbitrary permutation. Okay, so an arbitrary permutation of S. All right, so think about this as like a persuasion process, right? So I want to convince you that the algorithm's correct. And then I say, you know what? Why don't you just pick your favorite permutation? I'm going to show you that that particular permutation will be output by this algorithm with exactly the probability of 1 over n factorial. So that is the claim here, right? All right, so let's write down the goal, the probability that, A is equivalent to this sequence at the end of the algorithm, right? So I want to prove to you that the probability is precisely this. Okay, so if I do not manage to do this, any discrepancy will collapse the whole claim. Okay, so I have to prove, the probability is precisely that. Okay, so we're going to do so by induction. All right, so first of all, if n is 1, and then clearly there's nothing happening here, right? No swap. Okay, so the lemma is vacuously true, right? All right, so let's assume that the algorithm is true. I mean, sorry, this algorithm is correct, and the claim is true for M, B, and T. Let's assume that this is true, and then we will prove. Okay, let's say this is true, and then we'll prove that true also for M, B, and T plus 1. Okay, so this is our goal here. Okay, good. So how do we do it? Okay, how do we do it? All right. Now, as you can see here, we'll be talking about this A, but the content of this array keeps changing inside the algorithm, right? So in order to avoid confusion, I'm gonna define this AO. So this AO is the original A, the initial A, at the beginning, right? At the beginning of the algorithm. So that's all right? So this is because AO never changes, right? Because that's just a snapshot of the content there. Okay, very, very nice. Okay, well, since I have already taken a snapshot, I have every right to say, well, what is the last element of this AO? Okay, T plus 1. So that's basically N, right? That's the last element, right? Because, well, there's no ambiguity here because as I said, AO is the original permutation, all right? So that doesn't change because that's been finalized. So I'm taking the last element. Basically, I'm saying the last element of the original array. Okay, very nice. Okay, well, let's look at this sigma that you have chosen to start the whole argument with. Okay, well, this sigma has to include this y somewhere, right? Somewhere, although not necessarily at the last position. Okay, so I have to say well, I can say, where is it? And you have to give it to me. Okay, let's just say that, this y is here, and this is the x position in your sigma. Okay, so this defines x. Okay, so this defines x. All right, so this should be fairly clear, right? So there are no words. So if you look at this picture, I believe you can understand what I'm saying. All right, so once again, the logic goes like this. I have already defined y, and I said your sigma, which is a permutation of S, all right, will have to contain y somewhere, right? So tell me the position, right? So that's x. Okay, very nice. Well, now there are two possibilities, and I will prove only one of them. Okay, so let's say this is the first case, case 1. Okay, case 1 says x is not t plus 1. X is not t plus 1. Okay, so your sigma, which contains x, not at the last position. Okay, but in the original array, AO, x was, at the last position. Okay, so this is case 1. All right. This case 1 or case 2, case 2 basically says x is equal to t plus 1. Okay, so case 1 or case 2 depends on your choice, and also it depends on the original array. However, it has nothing to do with the algorithm itself. You see what I'm saying? Okay, so basically there are two subproblems you have to analyze separately. You have to prove that this claim here, this goal, right? So this probability 1 over factorial will have to hold true not only for case 1 but also for case 2. Okay. However, these two cases, they've got nothing to do with each other. Okay. All right. So I'm going to prove case 1 and case 2. I think that will be very good exercise for anyone who likes to understand. Okay. More. I mean. Okay, so let's think about this, right? Well, you see, this is the event this I'm interested in, right? So A equivalent to sigma at the end of the algorithm, okay? All right, and then I will give you a very precise if and only if condition for that event to happen, okay? So now let's do this together, right? So A is precisely sigma if and only if, okay? I'll give you two conditions, and both conditions will have to hold true, okay? If and only if, all right? So the first condition says, what happens right before the last iteration starts? Okay, what should be the content? What should be the content of A at that moment? All right, so this is the first condition. So I'm going to write it down, but before I do so, let me emphasize that this condition concerns the moment right before the last iteration. Okay, so if I ask you, what is the value of I for that iteration, everybody should tell me exactly t plus 1. That's n, right? So n is t plus 1 here, right? Okay, so the first condition says, well, right before the iteration t plus 1, okay, the following should be true if I compare A and sigma. Okay, if I compare A, so this is A, right? Now this A is not AO, right? So this A is our array A, which keeps changing, but this is the content of this array at the snapshot, which is right before the start of iteration t plus 1, okay? All right, so if you look at this A, the last element is Y because at this moment, the algorithm has not yet touched the last element yet, right? Because this algorithm processes every element from left to right, right? So every iteration it processes the next element. So if I stop right at the moment before the last iteration, you know that this element Y has never been touched, right? So Y has been sitting at the last position right from the beginning, right? So it's currently it's still there, okay? Now, another thing I want you to look at is this X, the position X. Okay, this is position X. I don't care what element is sitting there right now, but there gotta be some element, okay? I don't care about that, okay? All right, so if I compare this array to sigma, by the way, the length of both arrays is precisely n, which is t plus 1, right? So if I compare these two arrays at this moment, by the way, sigma never changes, right? Because it was chosen by you, but A has changed to this state right now. If I compare these two arrays, what should I see? Well, you told me that Y is at position X because that was how X was defined in the first place, right? All right. But what can I say about the other positions of sigma? Okay, can you help me out here? Okay, well, I don't know about you, but if you do a little bit of analysis, I believe it's pretty clear that you should have the following setup. All right, so what do I mean by this? You see, AX, this shadow, this box, shaded box, right? This box with the shadow. Whatever element you have there will have to be the last element of sigma. How do I know? Well, this is because I know that the algorithm is going to perform just one swap. You see what I'm saying? And that swap has to involve the last element because that's just how the algorithm works, right? And therefore, if Y has to go over there in the last iteration, and there's only one possibility, right? So this shadow element at the position of X will have to be moved to the end of sigma after the last iteration, right? Okay, so what can I say about the other positions? Well, they will have to be identical to each other. Otherwise, as long as this condition is not true, and then there's no hope for this event to occur. You see what I'm saying? All right, so for this event to occur, this is the first condition that must be satisfied, right? So this is something that I can assert about the content of A at the moment, right before the last iteration, right? Is that cool? All right, good. But this is only the first condition. You see what I'm saying? There's another condition that has to occur as well. What is that? What is that? How does the last iteration run? You know the last iteration is going to perform a swap, right? But don't forget, the swap is determined by one very important value, right? So look at the algorithm, right? You've got this value R here. You see what I'm saying? So this value R will have to allow you to perform the swap in exactly the way that I have already explained, right? You see what I'm saying? All right. So you, therefore, the second condition we must have is R is precisely X. Okay. If R is any value different than X, and then there's no way, there's no way A will be equivalent to sigma. Okay, as I said, this is an if and only if condition. Challenge me if you want. Okay, yes, please.
Excuse me, we do not need to write explicitly the shadow plus R equal that is AX equals to sigma T plus 1 because this is an if and only if condition. If this will
Well, implicitly, I require, this is not written down, right? But if you look at the Y region, every corresponding element in at every position, right, every corresponding position will have to be exactly the same in A and in sigma. You see what I'm saying? Yes. So here you already have n minus one, n minus two positions. T minus one. You have, so you've got T elements from here to here. You see what I'm saying? Okay. But T minus one elements have already been fixed, right? So there's only one shadow element, right? So that's why this shadow element will have to be sitting at the end, right? Okay. Good. Okay. Yeah. If and only if, right? So chew on it if you want. If this is not true, and then my proof collapses. Okay, so this is my proof. It could be wrong, uh, but it looks pretty good to me. Okay. All right, good. Now let's analyze the probability for every condition to happen. Right? Okay. These two conditions are independent, right? So we can analyze them separately, right? The second condition is pretty easy to analyze, right? Because this R is a random value, a random integer from 1 to T plus 1. You see what I'm saying? Okay. And therefore, the probability for the second condition to take place is precisely 1 over T plus 1. Okay. Now, how about the first? How about the first condition? How about the first condition? Well, that's the difficult part. So that will be difficult unless you use our inductive assumption, right? Okay, so you see, very importantly, we've been assuming that the algorithm is correct for any array of size t, right? So if you look at this is sigma, look at the prefix, right? The including the first t elements. What is that? Well, that's essentially the output of this algorithm on that prefix. I'm so sorry. I mean, the content of A, right? The content of A is essentially the output of this algorithm on the first n elements, okay, on the first n minus one t. Okay, so there's this n and t, very confusing, right? N is precisely t plus one, right? So what I'm saying is n minus one elements, right? Basically this part, okay? So so what we're saying is, the outcome of this algorithm on this size n minus one will have to be precisely, this part of sigma, right? The prefix n minus one of sigma, right? But that's only one of the n minus one factorial permutations, right? So according to our inductive assumption, we know that the probability would have to be precisely t factorial, 1 over t factorial. So if you multiply these two, you get 1 over t plus 1 factorial, which is precisely what we want. All right, good. Well, this is case one, all right? We just proved case one. now you have to think about case two, right? So case two essentially says, well, x is equivalent to t plus 1. I refuse to talk about it here because I don't have time, all right? But this is something basically quite obvious. Okay, so you just have to repeat the whole argument, but you change things accordingly. Okay, good. Very nice. So this is random permutation. Okay, so this is one algorithm for performing a random permutation, but we don't want a random permutation, right? We don't want a random permutation. All we want is a subset. Okay, except that this will have to be a random subset. Okay. However, as long as you can permute, you can take a random subset. Any algorithm that allows you to generate a random permutation can be utilized to generate a K subset randomly. Okay, good. All right, so that's exactly the reaction I'm expecting from you. I keep asking you questions. Okay, so that's exactly, um, that's just my little trick to encourage you to think. Yes, I think a lot of you have got it, right? So in general, right, if you are able to generate a random permutation, so let's say, so you can use n to obtain a random permutation of S. Okay, after that, right? So all you need to do is to say this random permutation, let's give it a name, right? So let's say this is A. Okay, A, okay? So, and then if you want to return a random subset, all you have to do is to return the prefix of A, including the first K elements. All right, so this is my notation for a subarray from 1 to K, okay, from positions 1 to K. All right, so all you have to do is to return the first K elements, okay? So I'm not going to prove that this is true. This is, too rudimentary, I would say, okay? So I would not bother with the details, except to say that this is correct, okay? So at this time, you already have an algorithm to perform WOR sampling in n time. Okay. Well, some students would be able to see that since you only care about the first K positions, right? You can actually avoid a lot of swaps. You see what I'm saying? Okay. Well, very naturally, this gives rise to the following refined algorithm. And so this is not for generating the whole permutation. This is for just taking a random sample set, right? So all you have to do is this, right? So for I from 1 to n, this is refined, okay? Refined algorithm, okay? From 1 to n, so you want to generate a random number, so this is the same as before, right? So if this R is less than or equal to K, and then you have to perform the swap. Okay, swap. Okay, and this algorithm is correct. So if I had given you the algorithm directly, it would have looked, I would say, a little weird. Okay, but now since you have already understood Fisher-Yates, I'm sure this is quite easy to understand, right? Because you can morph from the original algorithm to this one and convincing yourself that this is really just Fisher-Yates, truncated version of Fisher-Yates, right? So basically you don't bother with those positions that are irrelevant. Okay, very nice. Well, now it's time to talk about this reservoir algorithm. Okay, so once again, if I had talked about this reservoir algorithm directly, I would have a much tougher time explaining. But now nobody would get surprised to see the following algorithm. Even this refined version is still doing some unnecessary work, if you think about it. Okay, why? Because this is not just giving you the first k elements as a set. You see what I'm saying? This is actually giving you a permutation of those k elements as well. All right, so you're not just finding um, k sample, I mean WOR sample elements, you are actually generating a random permutation of those elements as well. Okay, so the third algorithm that I'm going to give you is this reservoir algorithm. Okay, so this is a very famous reservoir. This reservoir algorithm is a very, I think it's old. Okay, the spelling could be wrong. So reservoir algorithm is a very famous algorithm in computer science. So it says the following. Okay, so first of all, you just generate an array, initialize an array. This is an empty array of size k. Okay, all right. And then you want to initialize this array to just a prefix of a, including the first k elements. Okay, so this is a old, is what I mean, the original array. All right, so no random numbers are generated here. Okay, and then you want to start from k plus 1. Okay, and then you do what Fisher-Yates does. All right, so you generate a random number, da da da. Once again, this is from 1 to I. 1 to I. When I say da da da, it's verbatim, okay, to what I showed you before. Okay, and pay attention, right? This B is still an array, right? I still get the right to say BJ, B1, B2, you see what I'm saying? All right, so if R is less than or equal to K, you want to swap. Oh, I'm so sorry. This is not swap anymore because there's nothing to swap. So you set, okay, B R to A I. Okay, all right. So this time I would say it's not completely the same, the proof. Okay, if you want to prove the correctness, because after all, I have abandoned the permutation. At least I have abandoned the first k potential swaps. You see what I'm saying, right? So I'm generating fewer random numbers. Okay. However, if you want to prove that this is correct, I'm sure you have already got very strong intuition. Okay, so I would not go into the proof, except to say that you can also, once again, prove this, inductively if you want. Okay, so it's not precisely the same as what I showed before. However, it's very, very similar. Okay, good. Well, this reservoir algorithm is very useful, not only in this static scenario. Okay, so this is actually a stream algorithm. Okay, stream algorithm. Okay, so in general, if we have an infinite incoming stream, is what I'm saying. Just like I don't know, keyword search received by Google, right? So Google receives keyword search queries, a lot of them. So at the end of the day, Google might want to say, okay, let's take a sample, WOR sample of all those elements, right? So that's something that Google would do. Well, in general, you have an infinite string. You see what I mean? The size of the string is unbounded. I mean, you cannot really say, let's store everything in the string. Okay, the string size is unbounded, right? So a stream algorithm, the one very important goal of a stream algorithm is to limit the size of the memory that you use. Okay, so you have very small amount of memory compared to the length of the stream. On the other hand, you will have to do, amazing stuff, right? Such as taking a WOR sample of all the n elements, except that n is increasing indefinitely. You see what I'm saying? Okay. So this algorithm, this reservoir algorithm, is very, very appropriate for this setup if you think about it, right? Because all all it needs to remember is just this array B, and you can discard everything else, right? So every time an incoming element is received, you just perform this iteration there, right? So you either keep this element or you throw it away. And if you decide to keep it, you throw away another original element, right? So if you think about it, the memory footprint is just K, right? So this is something very nice about this algorithm. Okay, good. Well, let's go back to the static scenario. All right, so far you have understood a lot about WOR. Okay, so you know that WOR sampling can be done in n time. Well, actually, you know what? I will make it a little bit more precise because I don't care about the CPU time. I care about random number generation because usually that's the um, performance bottleneck, right? So you have to generate how many random numbers? Well, even if you use reservoir, you still have to generate n minus k random numbers, right? Okay, k is very large, and then of course you don't lose anything. But what if k is very small? You see what I'm saying? You'll be generating a lot of random numbers, right? On the other hand, if you think about WR, right? As I said, right? WR, again, the static setup, not the stream setup, okay? Static setup. For static setup, if you want to do WR sampling with replacement, having independence, you see what I mean? All you have to do is to generate k random numbers. N minus k, which is essentially n, because k is way less than n, right? So n versus k. Now you can see the discrepancy, right? So a very, very natural question is, hey, can we also do k random number generations also for WOR sampling? Okay. The answer is yes. Okay, so this is the last part of my talk today. Okay. Well, the answer is yes, not precisely though, in expectation. Okay, so I'm going to give you one way to achieve the purpose. So I will generate a WOR sample set of size k in big O of k time expected, okay, in expectation, okay. So this is another very fundamental technique. This is known as WR to WOR, okay. So this is essentially saying, suppose you are given an algorithm A. So this algorithm allows you to this is a WR black box algorithm. Okay, so WR sampling algorithm. So M is the K there, except that I don't want to use K because I want to use K for WOR, right? So you want to know that this algorithm takes a parameter, you can specify the sample size, and then it's going to just give you a sequence. Remember, it's not a set anymore, okay? It's a sequence, right? And this sequence is guaranteed to be a WR output, WR sampling output. Okay. So I want to use such an algorithm to generate a WOR sample set of size K, right? So to start with, let's try to set the parameter here to K, M to K, right? So we say AK, all right? Well, that's a good try, except that you will fall into an issue. Okay, and this issue also reflects one key difference between WOR and WR. You see what I mean? WOR, we want case distinct elements, all right? However, if you do AK, you might get a sequence containing some repeated elements, all right? And therefore, you cannot really say that, if I get the output of WR, I can immediately convert it to scale. Okay, good. Another reason why it might fail is that you could have some elements appearing twice. What are you going to do about that, right? Okay, so all these things will have to get cleared if you want to have a generic reduction from WR to WOR, right? But the goal is this, right? So I give you this A, I promise you there's this, black box algorithm. You don't have to care about how it's implemented. But I want you to get a WOR sample set by using this algorithm. Okay, you don't even get the chance to look at the original array. You see what I'm saying? All you have to do is to talk to the array by using this algorithm as the bridge. Okay, so that's the problem here, right? Nice. All right, so for our purpose today, I will assume that K is not very large. Okay, so in particular, I'm going to assume that K is, at most n divided by this number here, just some constant. Okay. Well, you will see why. This is 3 times e. That looks very strange, but if you look at if you study randomized algorithms, you see this a lot. Okay, so later you will know why. On the other hand, this is really, really a fair assumption, because if K is so large, it's already greater than n over 3e. And then, if I say big O of K, random number generations, it's essentially saying big O of n. You see what I mean? Because K is already so large, right? And if for such values of K, if you want to achieve big O of K, and then you can just take the original WOR, let's say reservoir, right? Algorithm. And so, that algorithm generates big O of n random numbers. But since K is this large, big O of n and big O of K, they're at the same level, right? Okay. So it's not an interesting case. And therefore, the rest of my talk will focus on this assumption. Okay. All right. Now, here's the algorithm. So the algorithm says the following. All right. So you want to first take a sequence. Okay. All right. So you want to take a sequence. Okay. So this sequence has length 2k, right? And then you extract, let's say, as distinct. So as this distinct is the set of distinct elements from sigma. Okay, so you want to see how many distinct elements you have there. Okay, so if the number is less than k, okay, you repeat. You know what? I will write it like this. Okay, if it's larger than or equal to k, and then you do something else, which I'll explain. Okay, otherwise you repeat everything again. All right. In other words, if you do not get k distinct elements, you call it failure. Okay, if this thing has failed, you just discard everything and start from scratch. Okay, so keep repeating this until eventually you succeed. Okay. Well, as you can see, when this algorithm utilizes the black box, it does not really extract precisely k. All right, this is just to increase the success probability, which we'll analyze later. So it extracts 2k, a sequence of 2k length instead, right? Just to increase the chance that you might have k distinct elements there. So very importantly, we will have to analyze what is the success probability of each trial. Okay, so we will prove that each trial will succeed with probability at least 50%. At least 50%. Now, this is not entirely trivial. This is something we'll analyze later. Okay, but suppose that it is true. If I ask you how many iterations there will be in expectation, the answer will be at most 2. Okay, why? Because this is like you toss a coin heads or tails, right? And the heads probability is at least 50%. And then I ask you, how many times do you expect to toss the coin before you see it come up heads? You see what I mean? Okay, so the answer is at most 2. If it's exactly 50%, the answer is precisely 2, right? But if it's greater than 50%, then the answer is less than 2, right? Okay, so if that is the case, you will see at most 2 iterations will suffice in expectation, right? And each time you will be generating 2 times k random numbers, right? So overall, you will be generating big O of k random numbers in expectation, okay? However, you still have to prove that this is correct. This is another thing that I won't have time to talk about, except to say that, if you think about 2 different k subsets, there is a very high degree of symmetry here. Okay, you can try to prove that all the possible ways that will generate one set will also be able to generate another set through renaming of some elements. Okay, so this is the intuition. All right, but it's not completely trivial, except it's very tedious and it's very tedious. Okay, but you will be able to go through the details. Right. So this algorithm is correct. However, one very non-trivial thing is how come this algorithm will be able to succeed in each iteration, right? Will be able to succeed with probability at least 50%. Okay. Okay. So this is also related to a very, very common this bins and balls problem. Okay. So I will rephrase the problem in the following way, right? So you take 2K people, 2K balls, let's say, right? So you repeat this experiment, right? So you take a ball, you take it, and then you put it back, right? You repeat this 2K times, right? So what is the probability you will see K distinct balls, right? Okay, so this is a classical problem to think about. Okay. All right, so this is the thing I'm going to prove before we go. So I'll prove. Okay, so the probability for this A2K to return at least K distinct elements. Okay, so this probability is at least 50%. Okay, so this is the final claim that I'm going to discuss. Okay, so let's prove it. All right. Okay, so this S distinct, so that's a bit too verbose, too wordy. So I'm going to just say R. Okay, so R is S distinct. Okay, so R is the set of distinct elements that you have from those 2K elements. Okay. Well, you consider any subset of this S. Any subset. S is the original set, by the way. Okay, I'm just saying, look, this R is a random variable, right? You cannot say what is the value of this R for sure. But on the other hand, if I first fix a subset, and this subset is T here, okay, and then I have the right to ask you what is the probability of R being T. Okay, so this is the reason why I want to talk about this T. So once again, R is a random variable, right? Because that depends on the output of this A2K, right? So I want to study this probability. I fix a particular subset, this T, okay? And I want to understand what is the probability for this R, the set of distinct elements, right, is precisely T. Okay. Well, this probability we can analyze. Okay, look, if this set T has size, let's say small s, it contains s elements, right? I don't want to analyze this probability precisely, but I can say that its probability will never be larger than this number. Okay, Why? Well, think about it, right? If those 2K trials, right? 2K experiments, right? And those 2K elements that I obtain, from this algorithm A, right? All of them will have to fall into this set T that you have fixed. You see what I'm saying? Okay. Will have to fall into, right? So that is a necessary condition, but not a sufficient condition. You see what I'm saying? All right. Because some of those elements, I mean, some elements in T may never get sampled, right? But on the other hand, as I said, it's a necessary condition because for R to be equivalent T, and then for sure, all the 2K trials have picked up elements from this set T that you have chosen in advance, right? So if you think about it, if I take one element from S uniformly at random, the probability for this element to hit your set T is precisely S over N, right? Because your set T has S elements there, right? And therefore, I can claim this upper bound for this probability, right? So R, B, and T is at most S over N to the power of 2K. Okay. All right. And then, well, with this observation, I can analyze the probability for R to be less than K. All right. So this is the probability we want to analyze. We want to argue that this probability is less than 50%. Okay. So how do we do this? Well, I think some of you have already seen what is coming. So basically, I will be looking at all possible choices below K. You see what I mean? Because if the size of R is less than K, and then there are only K minus 1, and there are only K possible choices, not K minus 1. 0, 1, all the way to K minus 1, right? So this is precisely the sum of this, let's say S here, okay, small s, okay? The sum of these K different probabilities, okay, good. All right, so this S, right, this is size from 0 to, from this 0, it cannot be 0, okay, because you have to take at least one element. So it's from 1 to K minus 1, okay? All right, now let's analyze a particular S. If I say, let's look at subset size S, and then I think about how many different T's can have this subset S, right? So I know I have, at most, I have exactly N choose S different T's. And for each one of them, the probability for R to be equivalent to that T is bounded by S over N to the power of 2K. Okay, so this is using the observation that we said before. Okay. All right. Now, I have my lecture notes, right? There was a homepage for this. So if you go through the derivation there, you will be able to see that this is actually upper bounded by this number here, this fraction here. Okay, so I'm not showing you the derivation details, okay? But all these details are there in the lecture notes, okay? On the other hand, we know that K is at most this threshold, right? So this basically tells you that, E, right? Basically tells you that EK over N is at most 1/3. That's what I mean? And therefore, this is less than or equal to 1/3 over 2/3, which is 1/2. Okay, so this proves that every iteration will succeed with at least half probability. Okay, good. Now, a few more remarks and then we're good to go. So if you look at this algorithm, right? So this WR to WOR method, right? So it will be able to generate fewer random numbers. However, this algorithm does not really replace reservoir. Okay, it does not really replace reservoir. Okay, as I said, the reservoir algorithm has this excellent property that it requires seeing every element just once. And also it's able to use a memory footprint of only K, right? And these properties are not really shared by this WR to WOR map.